All right, so let's jump over to OneNote and get started. So this is the test one review. The first thing we looked at was Riemann sums. So we'll just start by doing a Riemann sum. So let's say, estimate the area below. Let's say f of x equals e to the, let's say x divided by 2 from x equals 2 to x equals 5 using, let's say A, we'll start with 4 left rectangles. And then part B, we'll do 4 right rectangles. So again, the main thing here is to figure out delta x and your interval, which will be the same on both parts. So delta x here is found by taking the length of our interval, 5 minus 2, and subtracting by the number of rectangles we want to make. So that comes out to 3 over 4 or 0.75. So then we want to create our interval. So you start at your first 0.2, and then you just add 0.75 each step until you get to 5. So we have 2, 2.75, 3.5, 4.25, and 5. And so for the left rectangles, we'll be plugging in the first 4 points into our function to establish the heights, and then we'll be multiplying by the width of our interval, 0.75. So our area estimation here will be 0.75 times f of 2, which would be e to the 2 divided by 2, plus e to the 2.75 divided by 2, plus e to the 3.5 divided by 2, plus e to the 4.25 divided by 2. And then you can just plug all that into your calculator. And again, I'm just kind of making up this problem on the spot, so I have to type it all in. That's okay. So we end up with about 15.6. 15.60 if you rounded to 2 spots, which is usually what I round to. And then B, we want to do the same thing, but with right rectangles. So we have already established our delta x and our interval, but for the right rectangles, we'll be starting at 2.75 and finishing at 5. So this is the left, what we're using for the left, and for the right, we'll be using these points. So the area here is 0.75 times e to the 2.75 divided by 2 plus e to the 3.5 over 2 plus e to the 4.25 over 2 plus e to the 5 over 2. And I'll get an approximation there as well. So this one comes out to 22.70. So you can see actually for this example, the curves are quite a bit apart. So a true area approximation, if you wanted to establish one using these two, you'd probably take the average of them. But if they just ask you for the 4 left and 4 right, that's what you'd get. And the reason being is just that exponential functions grow very fast. So e to the 5 over 2 is much, much bigger than just e. Okay, so for the second one, essentially we just want to make sure, establish that you understand the integration notation. So we might have some picture where you're just given areas. So say we have like, I don't know, some points. Something like this. So I don't know, we could call this point A, B, C, and then this last point here, D. And then say we know the area is like 8, 3, and 1. And we could just say, figure out what the, find the value of each integral. And, we could call the function f of x again, using the picture. So something like this. And let's say A, maybe we want the integral, let's say from B to C of f of x dx. Well, B to C would be the area there that's given by 3, but because it's below the x-axis, we know it should be negative. So that would be -3 for the first one. Maybe part B, you would say something like the integral. Let's say we wanted to go the whole strip from A all the way to D of f of x dx. Then you would just add them all together with their appropriate sign. So you would have 8 because it's above, then -3 because it's below, and then +1. So that would be 9 minus 3, which is 6. You could also, do some other things. You could say, like, maybe what is the integral from A to D, but let's say I use the absolute value of f of x. Well, if I use the absolute value, that's going to turn all of them positive. It would actually take all of your, it would take the part from B to C and reflect it above the x-axis. So you would only have positive y values in that diagram. So this would be 8 plus 3 plus 1. So 11 plus 1, which is 12. And again, these things are pretty easy. You just have to remember that as you're going from left to right, your areas are positive if they're above the x-axis, and below they're negative. If you go the opposite direction, they'll also turn negative. So let's say I wanted to go, let's say part D, let's say I'm integrating, but I'm starting at D and finishing at C of f of x dx. Well, what is this doing? What I'm doing is I'm just looking at that last segment, that area with 1, but I'm going the opposite direction. So because I'm traveling in this direction, that's going to flip the convention. So instead of being +1, this will be -1 because we're going the reverse direction. So keep that in mind too. So other than that, though, usually those questions are pretty easy. Okay, and then pretty much the rest of the test is just a bunch of integration. So we start with some basic formulas, then we move our way to substitution, and then finally parts. So 3, maybe we want to integrate 8x cubed minus 6x plus pi dx, something like this. We're just using the polynomial rule, so we're going term by term, add 1 to the power, and then divide by that number. So, and then our constant pi, you just tack an x on there. So this would be 8x to the 4th divided by 4 minus 6x squared over 2 plus pi x plus a constant of integration, which this simplifies a bit to 2x to the 4th minus 3x squared plus pi x plus c. So that's a general one that shows the polynomial rules. Then maybe we have one that shows some of the exponential and other rules. Maybe we have the integral of, say, let's say e to the, or maybe let's make it a little more complicated. Let's say 9e to the 6x minus 12 over x. So for this one, we're just splitting them up into the two different parts. So remember the rules here. So the integration rules. So for the exponential e to the kx, the e to the kx rule is this just becomes e to the kx divided by k. Then, I have plus a constant here for all these, but, in general, if it's indefinite, you need to add that plus c. And then the other one is the integral of 1 over x dx is the natural log of the absolute value of x plus a constant. So we just have each one of those rules here. So the first one, we'll have 9e to the 6x divided by 6 minus 12 times the natural log of the absolute value of x plus a constant. And then, this can simplify to 3 over 2 e to the 6x minus 12 natural log absolute value of x plus a constant, something like that. Okay, so any questions so far? Okay, so the next two are word problems from the net change and the average value sections. I'm going to do essentially the same problems. I'm just going to adjust the numbers. So we're dealing with different functions. So 5, suppose R of t equals 5.2 times e to the 0.2t models the number of bacteria in a colony in thousands. Actually, this has to be a rate function. So it models the number of models, let's say the rate bacteria grow. Well, you have to grow on the next line, so replace that. Grow in a colony in thousands per hour. How much did the bacteria increase in the first 4 hours of the experiment? So this integral would just be the first 4 hours. So we're going from 0 to 4, and then we just use the rate of change function that they've given us. So 5.2 e to the 0.2 t dt. And again, this is a pretty easy integration. You just take the 5.2, divide that by 0.2, and then again, we're multiplying by e to the 0.2t, and we're going from 0 to 4. This is a definite integral, so we don't have to worry about any plus c's or anything like that. 5.2 divided by 0.2 simplifies as well, so that simplifies to 26 e to the 0.2t. from 0 to 4. So we have 26 e to the 0.2 times 4 minus 26 times e to the 0. So we get some approximate number. So something like 31.86 thousand bacteria. All right. Any questions there? All right, let's move on to number 6. So suppose, let's say f of t equals, I'm going to simplify this one a bit, 65 plus, say 0.4t gives the temperature in a city t hours after midnight. So let's say find the average temp from 4 a.m. to 2 p.m. So one thing to recognize here is if the t value is t hours after midnight, that means 4 a.m. is just t equals 4, but 2 p.m. is going to translate into t equals 14, right? Because noon would be 12 hours after midnight, which is 12, and then 2 p.m. would be 2 hours after, so that would be 14. So the average temp, remember what you do is you take, this is just the average function value, which is the length of the interval that we're working on. So it's going to be 1 divided by 14 minus 4 times the integral along that interval. So from 4 to 14 of our function measuring the temperature, which is 65 plus 0.4t dt. And then this just becomes a basic polynomial integration. So we have 1/10 times 65t plus 0.4t squared over 2. So 0.4 divided by 2 is just 0.2. So 0.2t squared from 4 to 14. And then we just plug in the numbers and subtract. So we have 1/10 times 65 times 14 plus 0.2 times 14 squared minus 65 times 4 plus 0.2 times 4 squared. And we'll see what that comes out to. Here, I'll do it piecemeal. So 65 times 14 plus 0.2 times 14 squared. Whoops, hit the wrong key. So we get 949.2 minus 263.2. So we get an average temp of 68.6. And this was in Fahrenheit, presumably. Okay, so the last four are just going to be 2 integration by substitution and 2 integration by parts. So we'll just go through that. Any questions so far? Let me check and make sure no one's asked anything in the chat. Don't see anything, so we'll continue. So 7, let's say we're integrating, I don't know, 8x times 2x squared minus 11 to the 10th power, something like that. So our substitution is just going to be letting u be the polynomial. Here, 2x squared minus 11. So then du will be 4x dx. And then usually the easiest way for us to do this is to just solve for dx. So divide by 4x. So du over 4x is dx. And then remember, usually we make our substitution using this first one, u, and what dx was down here. So our integral will become the integral of 8x times u to the 10th times our du over 4x. So 8x over 4x just becomes 2. So our integral is 2u to the 10th du. And that's easy. Just add 1 to the power 11 and then divide by 11. So we get 2u to the 11th over 11 plus a constant. And then we can change that u back to an x. So 2 times 2x squared minus 11 to the 11th power over 11 plus c. And that would be the antiderivative. Maybe let's try something like the integral of, let's say 5x squared times, let's say times 3, or let's say 7 to the let's say just x cubed dx. Okay, so here we want to let u be that exponent. So we want to let u be x cubed, as we normally do. Then du is 3x squared dx. So du over 3x squared is the value for dx. So again, using the first and third parts, we make our substitution, replacing the exponent with u and the dx by du over 3x squared. So our integral becomes the integral of 5x squared times 7 to the u times our du over 3x squared. So what we end up with here when the x squareds cancel is 5 over 3 times 7 to the u du. Okay, so what we need to remember here is, so recall another one of our rules is the integral of, say, a to the t power is 1 divided by the natural log of a times a to the t. So maybe that looks confusing. I don't know. I was going to do it without parentheses at first, and then I changed my mind. So maybe I'll just... So this is the rule for exponential functions that are in the standard form. All the ones we've seen so far were in the form of e to some power rather than a different base to some power. So what's going to happen is we're just going to get that 5/3, and then we're also going to have to divide by the natural log of 7. So we get 5 divided by 3 natural log of 7 times 7 to the u plus a constant. And in this case, if we want to switch back to x's, we would have 7 to the x cubed power plus c, and that would be it. So those are two substitutions. Let's go ahead and work through some integration by parts. So let's say we want to compute the integral of, I don't know, 12x times e to the 3x dx. For this setup, when you have a polynomial times a exponential, usually the polynomial is what becomes u, and the exponential becomes the dv. So du would be 12 dx, and v would be 1/3 e to the 3x. So then what is the setup? Well, we take u times v, so 12x times 1/3 e to the 3x, and then we subtract the integral of v multiplied with du, so that would be 12 times 1/3 e to the 3x dx. Again, I'm kind of showing every step here instead of simplifying along the way. So 12 over 3 is 4, so we have 4x e to the 3x minus the integral of 4 e to the 3x. So we have 4x e to the 3x. And then to integrate the second part, you again divide by 3. So we'll have 4 over 3 e to the 3x plus a constant. And the last one other integration by parts. So we have the integral of 5x squared, natural log of x. So when you have a polynomial or a power function times a log, the choices kind of flip-flop. So u is going to become the log, and dv is going to be 5x squared. So du is 1 over x dx, and v would be 5/3 x cubed. So then our integral, we do u times v, so we have 5x cubed natural log of x divided by 3 minus the integral of v times du. So we're going to have 5/3 x cubed times the 1 over x dx. And you'll be able to cancel one of the x's there. So we have 5x cubed natural log of x over 3 minus the integral of 5/3 x squared dx. And then the antiderivative there is going to be x to the third over 3. So we'll have our 5x cubed natural log of x over 3 minus 5 over 9 x cubed plus a constant. And that would be it. So we'll stop the recording here.